Well, about 3 years ago, Danielle and I did a video, which you can see here, on our old house and how we identified all the big power draw items and how we were going to design our new off-grid solar powered home to avoid the high energy consumption of a modern home. Well, let's see how we did. When designing and sizing a solar system for your house or any type of renewable energy system, oftentimes you hear people say, take your electric bill and size it based on your kilowatt hours per month. Well, I kind of think that's backwards. Okay, I think what you ought to do is go through your house and find out your power demand and decrease it as much as possible, and then go and design the system for you. And that's what we did in this house. We went through the old house and looked at how much things were drawing power, and we estimated. Now, what we've done here is we estimated, we designed, and then, and you can get these on Amazon and on the storefront, you can get a DC watt meter and an AC watt meter. These are tools you can use to determine exactly how much power you're using, the actual values as opposed to the estimated values. So let's see how we did that. Here we have a DC watt meter. I put two XT60 plugs on either side of this, and that allows me to plug it in line with the refrigerator and freezer. As you can see on the display, it has alternating information. Up in the upper left is just current amps being produced. Now that's TE is time elapsed, WH is watt hours, peak amperage there, minimum voltage there, and peak wattage, and then time elapsed again. So it cycles through those. On the right side, the upper right, you have the volts that it's taking in right now, and then the watts, the current watts, so around 56, 59 watts there, and that's about it. You can basically come down and see this one's been running here. Let's see, there's minimum volts, there's peak watts, there's time elapsed, 12 hours and 44 minutes, 10 amp hours, and 278 watt hours on this freezer in the last, well, roughly 12 hours. If you excuse me, I'm underneath the desk right now. This is the AC watt meter. It has a sleep mode, so the screen goes black until you actually hit it. And then you start off with the voltage and the frequency, which is 60 hertz. And then we look here at the amperage that's coming through right now. And this is the star length that's plugged into it. Okay. We have the lowest wattage that it's seen since it's been plugged in, and we have the highest wattage we've seen since it's been plugged in, and that's typically on startup. When it moves that antenna around, it uses quite a bit of wattage to do that. Okay, then we go to an overload setting, which is set by the factory. You can change it if you want to, but I don't have anything that big. I left the overload right there at 3680. Now we have current watts coming through the system, okay, 52 watts. Sometimes you'll see 60 on that. Sometimes it'll drop down. Starlight kind of goes up and down during the day. We also have a sleep setting at night, and that's why I've been running this thing for, well, for how long have I been running it? It's been 1 day and 13 hours. See, every 24 hours it resets to 0, and then it goes 1 day, 2 day, 3 day, 4 days. So that means it's been on for 1 day and 13, almost 14 hours so far. And it's used up a total of 1.475 kilowatt hours. So that's very nice because you can determine how much kilowatt hours it does per day, per week, per month. And so since I'm trying to track everything per day, I will translate that time into kilowatt hours per day. And for this, it's going to be about 1 kilowatt hour per day, roughly, and we'll see after 2 days what we get. And that's it. It goes back to this setting. Now, if you unplug this, it maintains those numbers and will just start right where you left off. But if you want to reset, there's a little reset button right there. You can hit with a paper clip or a pen or pencil or something like that to get in there. Really like this piece of equipment. It's been very useful in monitoring my loads. So this is yet another tool in my arsenal. It's called an amp clamp. This is from Klein Tools, and it allows me to monitor power going through wires. Now you have to select either the positive or the negative. You can't select both wires. So negative 3.9 or 4, that means power is actually going into this battery, okay? If it was positive, then power would be coming out of the battery. So it's negative, that means this battery is being charged. So this is one battery taking in 5 amps, and the second battery taking in another 5 amps. And the other thing I can do is I can come over here and I can, for example, look at the power going into the DC. Sorry, I was moving things around. Okay, so this basically has power. I'm using 4.8 amps of DC power in the house right now because this actually goes to the DC distribution box that I have for the rest of the house. So the house is using roughly 4.8 amps of power. And then I've got amperage coming in through the charge controller, amperage going out through the inverter, and then the excess is going into the battery. So that's a way to monitor your power in and out of all these systems. We are down in the utility room, and I just wanted to show you my midnight charge controller. This is the power coming in from the solar panels. I have a 2.8 kilowatt system, and it's about 9:30 in the morning. So the sun is kind of in and out today, so I'm not really pulling in a whole lot of power, but you can see I'm getting about 1,600 watts right now from that system. And down here, you have kilowatt hours. This is kind of what I monitor because this resets at midnight and it tells me how many kilowatt hours I take in a day. So in the summertime, you're looking at about 16 or so kilowatt hours. In the winter time, about 8.5 kilowatt hours on a sunny day, or 8 kilowatt hours. So you can see you get a lot less in the winter time. And then when clouds roll in, you may get as little as 1 kilowatt hour on a cloudy day because you get very little through there. Now I want to mention this too, that if there's any snow, let me hit this back on so you can see it. There's amp hours. If there's any snow at all, 1/4 inch of snow, it's white, it's reflective, you get nothing. It'll go down to absolutely 0 right there. You've got to clear snow off your solar panels as soon as possible because you will get absolutely nothing. And this bulk MPPT right here, what that means is it's taking every bit of sun it can to put into the batteries, and then it'll go to float when it's full, and then it'll basically just stop after it goes through float charge. It generally charges at 28 volts, so as you can see, 26.4 is roughly my full battery charge, so it's going to charge at 28 volts, so it's going to pull that up, and later on in the day it's probably going to say 27 or 27.2 before it goes to float. And so that's it. You can see it went behind the clouds. It's down to 23 amps and 600 watts, so not a whole lot of good solid sunshine today. And just adjacent to my charge controller is the inverter and the power box. This controls all my power coming in and power going out. So right now it says the inverter is on. It's inverting DC 26.4 volt into 120 volt AC power, and it's drawing 6 amps out of there. There's a lot of different features on this controller. I won't go through them all, but there's a lot of great information in this box as far as power flow and power control and charge controlling too. When I charge with a generator or anything outside, it comes through this box also. All right, so let's start with the washing machine. Now, you can get estimates online about what an average washing machine uses, but I would seriously recommend you get a watt meter and test your washing machine, because there are machines that'll run cycles that are 90 minutes long, okay? It uses a tremendous amount of energy as well as water, and water is energy too, and we'll talk about that later. So I plugged this in, and I came up with about 120 watt hours per load. Now, we're a larger family, so we do 6 to 8 loads a week. So you can pretty much assume we're doing a load a day for us. A couple of things to think about. First of all, we use quick wash because, again, I don't need a 90-minute cycle. And also, I do auto sensing, so it keeps the water level low. And the other thing you'll notice is it's not plugged in right now. I don't keep this plugged in because washers are one of those items that have standby power, and for this, it's about 5 to 7 watts of standby power. Other machines may be worse if they have a computer or something up there. It's estimated that some standby loads are up to 40% of the entire power consumption of an item. And those are things that aren't used very often. So you got to watch out about leaving things plugged in. But we have a trick up our sleeve that we'll talk about later that can reduce that altogether. So let's go look at something else. You notice when I was showing you the washing machine, we did not have a dryer. A dryer was a non-starter. We looked at the consumption up north and we looked at the average consumption. Even a gas dryer is going to use about 1.5 kilowatt hours per hour, which means that when you dry your clothes, it can basically, once again, eat up your entire battery bank, even with a gas dryer. So we hang all our clothes outside. Right now, this is the uncompleted wallapini that we will be building later, and we're using it as a drying area for our clothes. It saves us a tremendous amount of power. Later on, we're going to develop a clothes hanging area outside, and we've got a lot of Amish friends, and I tell you what, they are the expert when it comes to drying clothes outside. And you know what? Nothing smells better than freshly hung clothes outside, especially your bed sheets. So I would not even consider a dryer if you're going off grid. Well, Danielle and I knew right off the bat that the refrigerator would be a major power draw because it's continuous operation. So the first step we took was we went with a DC option. These DC options are much more efficient. They have super thick walls and they operate at about a quarter of what a normal refrigerator would operate at. So just by going the DC option, it saved us a lot of power. Now, this particular refrigerator estimates 760 watt hours per day. Now, when they test that, they test it with the door closed. And I understand why they do that because it's consistent and repeatable, and they have no idea how many times you're going to open the door. Well, we have teenagers. So as you know, the door is opened a lot, and they stand there catatonic staring at the food and not deciding what they want. So we decided to test it with teenagers, door opening all day long, and we got just over a kilowatt hour. So about 40% more than was tested with the door closed, which I suspected. But the other thing that happened in the 2 days that we tested, and I was glad it did, is Danielle went shopping. And when she went shopping, she comes in and she fills up the entire refrigerator. And when you do that, you're putting warm things in that refrigerator, and the refrigerator has to cool everything down. I measured how much it took. It took about 300 to 400 watt hours just to cool that stuff down. So it actually increased my usage in those 2 days, so I got a more conservative estimate of the power. And like I said, it's just over 1 kilowatt hour. Probably normally it's around 1 kilowatt hour. And so I'm very happy with this refrigerator. Here we are with the SunStar 21 cubic foot freezer. It's quite the monster, but it's very efficient. They estimated 605 watt hours per day at 70 degrees Fahrenheit, obviously closed again. And believe it or not, when I ran that watt meter for 2 days, it came up to exactly 605 watt hours. Now, probably because I'm in the larder and it's 50 degrees in here, which is good. And I don't open this much at all, so the closed door estimate is pretty accurate. I'm very happy with this. Now, it may be kind of hard to see me, but I wanted you to see the antennas behind me. There is a cell booster and there is a Starlink antenna behind me. Now, out in the middle of nowhere, we didn't account for the fact that we would have no internet, and we didn't account for the power draw that we would have trying to get it. So, cell boosters, if you can get by with a cell booster, it's very energy efficient. That only uses about 100 watt hours a day, or about 1/10 of a kilowatt hour per day. Starlink, on the other hand, as great as it is to get you high-speed internet, it uses a tremendous amount of power. Over a kilowatt a day, about the same as my refrigerator. So that's about a quarter of my power draw every single day, and that's even when we use sleep mode from midnight to 6 a.m. So if you have to go Starlink, you better consider that in your power calculations. Now I'm outside by my cisterns because I want to point out probably the biggest power saving design that we implemented into this house, and that is water. When you have to move water, pressurize water, you have to use power
to do it, and people don't consider that. One thing we learned was when you collect rainwater, you use significantly less than the average American. The average American home uses 300 gallons a day, and even though we have a large family, we use about 65 to 70 gallons a day. So using less water it's directly proportional to how much power you're going to use to get that water into your house. The other thing is, because we collect rainwater and we keep it in cisterns that are high, I have to keep them in the ground to keep them from freezing. However, the bottom of the cistern is higher than the bottom of my basement. So I don't have to use a well pump. I can use what's called a booster pump to pressurize my tank. Now that booster pump is about 1/5 of a horsepower, and those of you who have researched wells will say, wow, that's a tiny pump, and it is. Well pumps can be up to 3 horsepower. So when you're looking at 1/5 of a horsepower as opposed to 1/2 horsepower, 1 horsepower, or up to 3 horsepower, it's a significant saving. Now, couple that with the amount that we use less water, and essentially I'm using about 1/10 of a kilowatt per day for my water. I'm going to say that again, 1/10 of a kilowatt per day. When I looked online at the average power consumption of a well pump, it said 4 to 6 kilowatt hours per day. That's unbelievable. It's 20 to 50 times higher than what I'm using. And in fact, 4 kilowatt a days would wipe out my entire usage here at the house. It would wipe out my battery bank. So I am certainly grateful that I went with a cistern design and a booster pump in the basement. It saved me a tremendous amount of power.
For our particular family, we have one power draw that, again, we didn't properly calculate when we moved here. We have 2 girls that are homeschooling, and they need to be on the computer and the laptop about 8 hours a day. So if you add the computer, the laptop, and Starlink, you're nearly 2 kilowatt hours, or about 30% of our entire power draw for a day. So if you don't need this, you could go to about 1% of that if you just use a cell phone and a booster for internet access. Something to think about. The other thing is, we don't leave this plugged in because the standby power on this printer is about 5 to 7 watts, which is pretty high actually. But the other thing is, when you actually use a printer, and it depends on what kind of printer you use, but that runs at about 900 to 1,000 watts to print pages. So we don't use it a whole lot, and when we use it, we plug it in, use it, and then unplug it again to save power.
Now, as some of you that follow us know that we have a wood cook stove, and that's what we cook on in the winter, but we are out in the summer kitchen, so I have a jacket on because it's kind of cold out here right now. But in the winter, we generally cook on the wood cook stove. In the summer, we cook out here to keep the heat out of the house. Now, we got a gas stove with no computer, no clock, no standby power, and we talked about that before. So we wanted the basic, simple stove. Now, the problem with this is we went to a regular box store, and the oven down there, the way it operates is there is an igniter in there. And that igniter is an electric igniter, and it's a resistance igniter that uses between 300 and 500 watts. I actually measured mine. It uses 375 watts. Now, that lights the flame. The problem is, and this is for safety reasons, that igniter never goes out. It runs continuous as long as you're operating the oven. So that's 375 watts continuous on a gas stove. And you can see the problem there. We thought it would save a lot of electricity, and it actually uses quite a bit of electricity. Now, what is your other option? There are off-grid sites that sell off-grid stoves. The difference is they're significantly more expensive, and what they do is they usually operate out of a battery. They usually have a 9-volt battery. Now, the 9-volt battery not only produces a spark to start the stovetop, it also produces a spark to start the oven, and it'll run off of that. So it uses very little power, obviously a 9-volt battery or maybe a D cell or something like that, but it doesn't even plug in. It's great for efficiency, but if you're concerned about safety, that's another matter. You may not like the fact that it doesn't run continuously and keep that flame lit. It's like the older stoves that ran on a pilot light or an electronic spark. So it's up to you. Are you going to pay for the off-grid one? Well, the benefit is
you get significantly less power draw from that oven. One of the main power draws we found up north at the other house was our septic aeration system. Now that aeration system was required by local code for a septic system, and they use a tremendous amount of power. They have an effluent pump and an aeration pump. And together you're going to run about 2,000 watt hours per day or more. 2,000 watt hours is a tremendous amount of power. It's half my power consumption in this entire house. And back to refrigerators, it could run 2 refrigerators. So if you're going off grid, a septic aeration system is almost untenable unless you have a big power system and a big battery bank. So we went with the composting toilets for several reasons, but this has a tiny little fan in the back, and the other one does too, and they run about 1.7 watts. And so I'm using about 70 watt hours per day. In other words, an aeration system would be 30 times the power consumption of these toilets. And that doesn't even account for the water. This is a waterless, and that one uses very little water. And you go back to a standard toilet, a standard septic system, and you're running gallons and gallons of water through there too. And we talked about that earlier, that water also consumes power. We're down here in the utility room, and this mess is my boiler system. Some of you know I have a wood-burning cook stove and has a boiler around it. Now, when we installed this, I had to get professional help. I didn't want to do it myself because it can be very dangerous. And I really wanted a fully DC system, but they weren't comfortable with doing that, and they didn't know how to get parts and stuff. So I allowed them to go ahead and put in an AC system that plugs in. And the pumps themselves don't use a whole lot of power. In fact, when I ran these, they're running about 2 amps or so. If I ran this for 4 hours, they don't run continuously, they cycle. If I ran it for 5 hours a day, if these pumps ran for 5 hours a day, that would only be about 800 watt hours in a day. But I don't know that I've ever had them run that long, okay? They just don't run that much because we have a very efficient home. On a sunny day, I don't have to run the boiler at all. Even on a cloudy day, I only run it in the morning and at night. So generally, I'm looking probably about 1/10 of a kilowatt hour per day to run this boiler system. Could be a little bit less with DC, but the big advantage if I able to switch this over to full DC is that I don't have to run the inverter when I run this, and we'll get to that next. I want to talk about another power draw that people don't consider, and it's the primary reason we designed our house to run off of DC power. Inverters. Inverters use a lot of standby power. Now this one says it's rated at 30 watts of standby. In other words, no load, it takes up 30 watts. Nothing plugged in, not doing anything, it's still going to consume 30 watts of power. I found that to be slightly more because I'm guessing it's the GFCIs that I have in the house, but in any event, what I've measured is about a kilowatt hour a day. Now, I always reference everything to my refrigerator. Again, that right there is another refrigerator, even if it's not running anything, okay? So if you have to run an inverter, you also have losses going from DC to AC. This is about 93.7%, so it's pretty good, but again, there's losses there. If you can run everything off of DC, you take in DC from the solar panels, you put DC into the batteries, and if you can run the equipment with DC, you don't have any of those losses. You don't have to waste a lot of energy with its AC power. So what I do is if I have several cloudy days, because my house can run completely without AC power, is I shut this down, all right? When I shut this down, of course, I lose my Starlink, my internet, but again, the Starlink is a huge power draw too. So when I shut AC power down in the house, I'm saving a kilowatt hour a day just to run this, and I'm saving Starlink, I'm saving standby power on any other things that I have plugged in there. So really, focus on DC, and I think you'll save yourself a lot of power, and you can really downsize your system if you stay away from AC power. It's nice to have it because you can run tools and you can plug things in. Great, but stay away from it. It uses a lot of power. So I said stay away from AC power, but that's easier said than done. In the United States, well, if you have a woman in the house, you're going to have things that plug into the wall. And the DC sourced items or powered items are becoming more popular, but we're not there yet. We have a few other things in the house that are AC powered too. Things like the vacuum cleaner, the air filter, the dehydrator, all of these things run off of AC power. We've got a mixer, a Vitamix, a toaster, an Instapot. Now, true, these are all convenience items really. You can get by and cook without any of these things. In fact, we hardly ever use this in the winter because we use our wood cook stove. But if you like the convenience of modern life, realize, in America at least, you're going to have to go with AC appliances because there's not a lot of DC options. Now, if you're looking for DC appliance options, you can go to off-grid sites. You can also go to RV sites, camper sites. You can go to semi-tractor trailer sites, people that sell stuff to truck drivers, and yachts, because all of those are run on DC. In fact, Danielle was hot this summer, so we got her a ceiling fan, and this is hardwired to the 24-volt house wiring system, so it's completely DC. It is a convenience, but it sure makes her happy, and that makes me happy. Now that we've looked at each individual item and its energy consumption, let's wrap that up into an easily readable graph for those of you who are not electrical engineers and have no idea what watt hours, amps, volts, and all that other stuff is.
Okay, so this is a breakdown of all our energy use for a normal day, inverter on, using the computers and Starlink. It breaks down the percentage that each item uses throughout the day. Now, I didn't really get too detailed on the DC usage, but I monitored the total house DC usage. As you can see on the right, the graph breaks it down in percentages, and on the left, you have each item and a total kilowatt hours. It's about 6.2 kilowatt hours per day. Now let's say I'm a little bit concerned about power consumption, so I decide to turn the inverter off at night, which also takes Starlink down at night, and then I ask the girls to cut down on their computer time a little. You can see I quickly fall down to 4.6 kilowatt hours total, which is about 1.5 kilowatt hours saved. And on a cloudy day, a lot of times I can take that much in. So let's say it's cloudy for 2 to 3 days. What does it take to run the basic house? DC only, no AC, so no internet, no computers. Well, as you can see, it drops precipitously down to 2.6 kilowatt hours. I can easily take that in on a cloudy day, so I could run indefinitely. This is where it's very helpful to know exactly how much power you're taking in to determine whether you have a surplus that day or a deficit, and determine what conveniences you want to live with and what conveniences you can do without, or whether you need to turn the generator on.
So let's talk about energy management. On a sunny day, I take in about 8.5 kilowatt hours of energy in the winter. That's the lowest amount I'll take on a sunny day because it only gets bigger in the summer. So I want to use that surplus because I'm only on a regular day, as you saw from the graph, about 6.2 kilowatt hours, so I have a surplus. Well, what do? Well, I get a bigger battery bank, which is very costly, and unfortunately I haven't been able to afford an extra battery. I'm looking into that. You can also do things physically to bank your power. In other words, on sunny days, you can vacuum. You can do laundry, and I do 3 or 4 loads of laundry on a sunny day. Not only does it save the power for a cloudy day, but the clothes dry better on a sunny day. I can use power tools. So on those sunny days, I try to use up that surplus so I don't have to use it on cloudy days. Now, what happens when I have a deficit? Well, if it's partly sunny, I generally get 6 kilowatt hours. It's not an issue. But if it's full clouds like today, I'm down around 2-3 kilowatt hours. Sometimes on a thick cloudy day, it's 1 kilowatt hour taking in from the solar panels. That's a pretty big deficit. Now, as you saw before, I can turn off the inverter and save quite a bit of power, and I generally do that. But still, I can only go a couple of days shady. And then I actually have to turn on the generator, or I can tap into my Bluetti power that's in the barn. And I do that quite often because if I'm not using power tools for several days, the Bluetti is fully charged, and I'm not using a lot of power in the barn. So I'll go ahead and charge these batteries with my Bluetti and use the solar panels that are on the barn. Something to think about.
Well, I hope you've learned a lot today. I want to say that overall we were successful. Our house up north ran about 35 kilowatt hours per day, and this one down here runs between 5 and 6 kilowatt hours per day. So we're less than 1/5 of the power consumption in this home. So overall we did good. We had some hits, we had some misses. We've learned a lot along the way, and hopefully by watching this video, you've learned and you won't make the same mistakes we did. Thanks again for joining us. Thanks for those who have subscribed, and if you haven't, please do so. Leave a comment. We love to learn. We love to share. So we'll see you next time.